even more so than atomic history, I think quantum history is critical for you to understand, because we need to understand how we get to the weirdness that is the quantum mechanical model. And so quantum history is a journey through that weirdness and trying to understand where these ideas come from. So we move into what we call line spectra and a gentleman by the name of Max Planck. So it's been known for centuries that certain elements give off certain colors when they're burned, that different color fireworks come from different chemicals. And there's lots of different things out there that can show you which chemicals produce which color. So a gentleman came along by the name of Max Planck that he said this has to be due to something in the atom or the elements that makes it give off these certain colors. Because they also knew about what we call line spectra, that the light that's given off by these elements as they're burned or energized doesn't create a rainbow when you shine it through a spectrum. It actually creates what we call a line spectra, that instead of having a band of red, orange, yellow, green, blue, and violet, that like if you take hydrogen and you shine it through a prism, you get this. You get a red line, a green line, a blue line, and a violet line. And that is called a line spectra. And every element has a distinct line spectra, like a fingerprint. This is important. This is how they figure out what's in a star, by looking at the line spectra of the light that's emitted. And so Planck was able to determine the frequency of each band of color. So Planck was then able to come up with an equation to relate energy to frequency. And this is his equation. E, which is energy, equals H, which is Planck's constant and has a value of 6.63 times 10 to the negative 34 joule seconds. Don't worry about the units, they're weird. And then F is the frequency. And so frequency, by the way, its unit is hertz, or 1 over seconds. And that kind of comes into play of canceling out the seconds and giving you joules for your energy. And so he then went a step further. And Planck said that the energy involved had to be related to some energy gap within the atom. And so he kind of came up with this diagram that if you look at a hydrogen atom, that basically the light's being given off as the electrons fall down from higher energy levels down to lower energy levels. And that he said, hey, these line spectra correspond to these drops from the third to the second, the fourth to the second, the fifth to the second, and the sixth to the second. So when you energize the hydrogen by putting electricity through it, you energize and all these electrons jump out of their ground state up here to the top. And then slowly they fall back down, and as they fall back down, they give off that energy in bands of light. And each of these gaps is constant. Like I said, it's like a fingerprint. It doesn't change. Hydrogen's line spectrum always looks like this. And so he said, well, the energy is constant, and it has to be a very specific amount. And he called that a quanta, or a quantum, plural is quanta. And he then said electrons will not change energy until it has that amount of energy, or it gives off that amount of energy. That is the magical amount of energy. Think of it this way, that if you're going to get in a plane going from LA to Tokyo, you're not going to want that plane to take off until it has the right amount of fuel on it, or a little bit more. So in the same way, an electron's not going to jump from this level to this level until it has that amount of energy to make the whole jump. It's not going to go halfway and then come back down. In the same way, you don't want your plane to go halfway and run out of fuel. That'd be kind of bad. So same thing here, that the electron, when it goes up, isn't going to want to jump until it has all of that energy available to make the whole jump. And then any extra energy is just left over. It's only going to use up that amount of energy. So that's Planck and quantums. So we got this amount of energy that's called a quantum. That's kind of where the name comes from. So along comes a little guy by the name of Albert Einstein. 1905, he's experimenting with shining different colors of lights onto a piece of metal. Sounds exciting, doesn't it? However, this leads to what's called the photoelectric effect. Now, out of everything that Einstein ever did, This is the one thing he won a Nobel Prize for. So it's a pretty significant experiment. So what Einstein noticed is that electrons would be emitted off of the metal if the light had higher frequency. So if he's shining blue light onto the piece of metal, electrons would come off of it, but if he did red light, nothing would happen. And this is independent of the light's intensity. So if he did a really, really bright red light, nothing happened. If he did a really, really dim blue light, electrons would come off. So it wasn't about how bright the light was, it was how bright the light was. It was simply the color of the light that mattered. And this is called the photoelectric effect. Light rays hit the metal, and then the metal emits electrons. Now, Einstein realized that this couldn't be explained by waves. And so Einstein really had to come up with something else to do here. And so he came up with the idea that light was actually small quantized particles called photons. And that's what makes up light. That light is both a wave, because we know that from certain experiments, but it also acts like a particle. And he said that the energy is quantized because the red light doesn't have enough energy to emit those electrons, but the blue light did. And it wasn't about intensity. It wasn't how bright the light was. And so he added this quantum idea and applied it. And so basically he said that if it had enough energy, it would then eject the electron. Just kind of like if that guy came at me, it would make me go away. Random picture of an elephant. All right. So Einstein begged this question: is light a wave or is light a particle? Because the photoelectric effect doesn't work if light's a wave. But then there are so many experiments with light that don't work if light's a particle. And so Einstein did the ingenious thing and said, well, it's both. At which point in time, most of us are sitting there scratching our heads going, huh? It's both? What? Well, it's true. And this is what is called wave-particle duality. And so light can act as both a wave and a particle, and it's both. That's a little wacky. It's a little weird. Okay, so this is kind of our first step into weirdness. Okay, well, unfortunately, it goes further. Okay, in 1924, a gentleman by the name of Louis de Broglie extended wave-particle duality to include electrons. And he said that electrons, in fact, are not actually just particles. They also have a wave nature to them. And this has been proven. They've actually determined the wavelength and frequency of electrons. So this has been proven. And so, so we've got this going on, and it blows the mind. And de Broglie eventually went on to even include us, all matter. All matter exhibits wave-particle duality. About the same time, Werner Heisenberg proposed the uncertainty principle. And the uncertainty principle states simply this: that both the position and the momentum of an electron cannot be known at the same time with certainty. Basically, it's kind of like a balance, which is what I have the picture here. Is that the more you know the position, the less you know its momentum, aka its speed. And then the more you know its momentum, the less you know its position, where it is. And so they kind of go in a balance with each other. The more you know one, the less you know the other. Amazingly enough, the uncertainty principle is what determines part of how stars age and how they behave and how they collapse when they collapse into a nova or a neutron star or a black hole. All right, so we've got some added layers of weirdness. So we're now applying what we learned about waves with light, and we're applying it to electrons. And all of this means that unfortunately we need a new model, because the Bohr model is no longer accurate. Because if electrons act like waves and we have uncertainty, we're not sure exactly where they are, then the idea of pretty little energy levels no longer works. Now, this doesn't mean the Bohr model gets discarded. The Bohr model is still helpful for simplistic senses, but when we're really trying to understand what's going on, it doesn't work. So, like I said, electrons act like waves, their position's uncertain, we've got problems. So, in 1936, Erwin Schrödinger wrote an equation that described the energy and position of an electron in terms of probability. And this is his crazy equation. Okay, it's called Schrödinger's equation, and we're not going into the math of this. I had a class on this in college, and it was brutally bad. And so it's definitely not a high school chemistry level concept. You just need to know that he came up with an equation that's all based on probability. Okay, so his model is then going to be used to create what we call the quantum mechanical model, which is our next lesson. Once again, focusing on the probability of where we think electrons are.